Let us review what we were talking about the last time. I always like to review in some detail, so in some sense you see everything twice. And in the notes I will always write a summary. So in a review, we are considering G, I would say always in this lecture, is a group. You know the axioms of a group now. And G cross X. So I'm saying that a pair Gx goes to G of X. This is a group action. So there are two words at the beginning of the subject, groups and group actions. We have the axioms of that and precisely written, so you know what that is. And we had a motivating example. So the main example to start with is to understand in this some good way, maybe in a little bit sophisticated way, the symmetries. You already know what this word means, even though it's in the title of our course, the symmetries of a square. So last time I drew a picture of a square. All sides are the same. That's what we have in mind for a square. As those of you who know me, I draw pictures all the time, so I have to have a picture, otherwise I can't understand anything. So that's a square S. And we decided we should view S as a subset of the Euclidean plane. Plane. I call this thing expression E. Maybe if it's not clear we're talking about a plane, I might put a 2 down here to remind you of the dimension. And so we have the idea that the symmetries of S are those symmetries of the plane which stabilize S. I'm using this word stabilize, it's a good word. S. Let me just say once and for all what I mean by stabilize means. It means, in other words, G of S equals S. It doesn't change S. It may change all sorts of other stuff, but it doesn't change S. So the set of G such that G stabilizes S should be the symmetries. Should this be a symmetry group of S? Now, of course, here, instead of G, where the heck am I talking about? G in the symmetry group of the plane. So everybody here is good in logic, and you see that I have a very bad circle here because I'm talking about symmetries of something in terms of symmetries of something else. And I don't understand what the symmetries of something else is. I don't even understand what the plane is. So we worked on that problem last time. So last time we worked on the problem. So the first identification or description, maybe description is a better word, of this two-dimensional Euclidean space is the two-dimensional affine space. Okay, I'm defining Euclidean space in terms of the affine space, which is okay, but I don't even know what the affine space is. So let's be precise about that. We talked about it. So the affine space, any affine space in general, is an affine space modeled on a vector space V is a set equipped with, and now here come two words again, a free, that's the one where we talked about, and transitive, so we use two free transitive action of the additive group of the vector space. Vector space has two operations. I call the one operation scalar multiplication because you're multiplying by numbers which are quite often called scalars. This could be a real number, but here the field of the vector space, in our case, doesn't need to be anything, is the real numbers. So if you take a basis of the vector space, you can identify the vector space with the plane R2. So affine space model on a vector. Free transitive action, let's go through that again. Transitive is very easy. Means that for any x you have, gx takes x and goes everywhere. So that means the g orbit of any x, no matter which one you choose, is the full space x. You go everywhere. You keep in mind the translations on the plane. You go everywhere. So v goes to v plus t. You know how you do it. If t, how this works is this is a picture of v. Here's a v, and here is t. And if t is something like this, maybe here's t, and then here's v plus t. Right? So that's you could go anywhere you want. Somebody gives you a point here, some guy gives you a point, you say, listen, I can easily get that, I just translate over and get it. Okay, so that's the notion of translating. Free means, I'll write it in language, the isotropy group, I'm not sure I used this word yesterday, but I'm not, it's a very important word. The isotropy group, Gx, that's a sub x if you can read it, Gx of every point x in x consists only of the identity. E. So what is this isotropy group? You know what it is. It's the stuff that fixes x in G. So this is the set of G that fixes, the set of G and G that fixes, which fixes x. and you check that that is a group, and it's called the isotropy group at the point x. I didn't write it here. Well, isotropy group of the point x is just the elements of a group which fix that point. So free means the isotropy group is nothing, it's trivial. The isotropy, well, it's the identity. The isotropy group is just the identity. That's free, that's the notion of free. So you have a free transitive action on state. And that means, of course, that A is equal to the orbit of any A for all A. Doesn't matter which you choose. We were joking around, it's good that Crystal's still sitting in the front row. We can use, also, it's nice to use her as a base point, right? So you take any A, that's Crystal, and we can move it all the way across anywhere we want, uniquely. Mr. Found, there's a unique translation to go from Crystal to Mr. Found. You see, we're living in an affine space. Really, I mean, we're living in an affine space. So, the translation for T to equal a point B, so this is Crystal. I don't know, AL or LE? AL. AL. How should I know? AL. And this is Mr. Pham. So you go from Crystal to Mr. Pham by a unique translation. Right? And you can go everywhere in this room by translation, uniquely. So this room is an affine space. That's good. I'm reminded, as I use this model of our room for an affine space, I was working with my grandson on Skype the other day, and he was learning to find the circumference of a circle. And so I wanted to introduce to him the notion of approximate. It's an interesting notion, given the circle, right? What is approximate? So at this time, his father, my son, was sitting with him and helped him do several things. He helped him take with a compass, or they made a compass with a piece of string, and they had the radius, and then they made a hexagon around by copying the radius around. Everybody has done this, I hope. Right? And then they measured the length of the radius, which it turned out to be 3. That's a convenient number, maybe. And so you add up the length of these sides, the 6 times 3. So my grandson it's okay with him. Everything's okay now. 6 times 3, he knows what that is. It's 18. And so I said, now let's divide everything in half and put these lines in here. And we did that, and we got 12 little smaller lines. And then we're trying to decide whether this 12 smaller lines, so you have 12 smaller lines, and then if you add up all the little lengths, what do you expect gets? And so it was a big calculation, and we got something like, I don't know what it was, but it was bigger than 18, as you can imagine. And then we did it again and didn't know, and so the word approximate came up. And he is only 6 years old, I think, and this was a new word for him in this context. Yeah, so my son is a very good teacher, I think. He's also a teacher, not a mathematics, a pianist. He said to the grandson, just think, you're approximately 7. And Frederick said, I'm 6.5. No, Alan said, you're 6.85. So it began, you see, and Frederick didn't care about approximating the circle. I thought it was a great idea, you know, a hexagon and all this stuff. We were getting some idea about successive approximation. But my son put it in real terms to Frederick. Yes, you're not just Approximately, you're 6.5, yeah, you're 6.85, that's neat. Let's take a look at what approximately means for your age, and he was very interested. Yeah, he couldn't care less about the circle. So we're the affine space, that's the little story. That's an affine space. Okay. And now we talked about certainly the symmetries of the Euclidean plane, of this Euclidean plane, certainly contain the translations, because they contain, let's even, we're adults now, symmetry group of this thing certainly contains the symmetry group of the affine space, two-dimensional affine space, in particular the translations. Right? Yes.
Why are the translations part of the symmetry?
Because I say. I say Euclidean geometry, if I'm talking about two figures in Euclidean geometry, any figure you want, if they differ, I want to know whether they're congruent in any sense at all. They certainly, if the two symmetries differ by, if the two, shapes differ by a translation, then they're certainly equivalent, right? Modulo symmetries. I'm just talking about something you learn when you're in kindergarten.
Do you define it that way?
I define it that way, but I'm also talking about the way Euclid defined it. I'm talking about the way you hear it in kindergarten. I'm talking about if anybody in his right mind looks at two shapes and asks yourself if this circle is effectively the same as this circle. Almost anybody, I think anybody in this room would say the answer is yes, because there's a translation which takes this circle to that circle. That's all I'm saying. Okay? And anyway, I get to say it because I'm the professor. Okay, yeah.
Is there a reason why we distinguish the Euclidean plane and the affine introductions?
Very good. He's saying, is there really anything different between the Euclidean plane and the affine plane somehow? This is, he asked the right question. So let us think about this. So certainly, so in some sense, I'm going to ask Mr. Weiss's question. And the question, is there any difference and maybe this is Maria's question, between A2 and E2. I think that's basically what you're asking, is it? Or between the symmetries on A2 and the symmetries on E2. Certainly the translations are symmetries here, and certainly by definition, and by my law as professor in this course, or by Euclid, the translations are here. Yes, Maria?
Didn't we define E2 to be...
Can you say louder?
Didn't we define E2 to be the affine space modeled after R2? Then, just by definition, they're the same, right?
I told you what the affine space is. It's the
So,
affine space modeled on R2.
yes, so if E2 is A2, then of course there's no difference between the two, right? Because we define...
A2 is a set. Are you understand? This is a nice discussion for people who have not yet been doing much mathematics. E2 is equal to A2 as a set. There is an obvious, yeah? But we haven't yet finished the notion of what are the symmetries of these things. And what I'm saying is, and I think we're homing in on a very important point, is to define anything, you have to know what the structure is, right? And I'm saying the structure is the group of symmetries. Yeah. That's why it's so circular, right? I mean, you're trying to say what is a symmetry, but in fact the structure is a symmetry. And she's always complaining, how do you know that's it? And I say it's it. I mean, okay. But I'm also talking classically, historically. Euclid, my grandson Frederick. I think it's clear, right? Yeah. Is there any other objections? I think it's a good discussion. Okay, great. So is there any, this is Mr. Weiss's question. And the answer is as sets. So the one answer is as sets. No. As sets? No. It is the affine space. But we're trying to answer this question here, what the devil are the symmetries of the square? And we say, well, they're the symmetries of Euclidean space which stabilize the square. So we go to Euclidean space and we want to know what are the symmetries of Euclidean space which stabilize the square. Then we ask the question, what is Euclidean space? And we say, at least at first, is a set, and with a little bit of structure, it's affine 2 space. Okay? And then we like Crystal so much that we say we're going to use her as base point, which we did yesterday. Right? I think we used as base point. It doesn't matter. You choose the base point as the center of the square, so that's the base point. This is we're going to use, we may choose any point we want. So we choose this as a base point. As a base point. And then, yes, and then we may choose this as 0 in the orbit, R2 of the base point. Right? Model on the base point. So in fact, then we have reduced, using the translations, to here 0 in R2. I'm being a little bit pedantic perhaps, but I don't think so. Okay, and then you say, okay, at least I know about the symmetries. So the symmetries of a symmetry group of E2 certainly contains the translations. But no translations stabilize the square. Everybody buy that? You agree? No translation stabilizes the square. I mean, I can prove it, but I mean, there's no sense of proof. It's completely clear, right? No translation stabilizes the square. Okay. So that means that means we only need to understand the symmetries of Euclidean space, which fix 0, so now 0 in R2, which we have now identified with the Euclidean space by the set of translations. Okay. Okay. Yeah.
And how how about something like a rotation? I mean, in the case of the sphere, we can only have 4 different rotations.
You're thinking, I think, I agree with you completely, but you're thinking, I think that's typical of us, we think too far ahead. In the end, we will find some rotations, and we will find some reflections, and so on, that you're seeing there. But what we're trying to do is understand this situation carefully, abstractly, because this is only a microcosm. This is a mini microcosm of understanding symmetry. And we will, in the end, say, well, you have the 4 rotations and 1 reflection or 2 reflections, whatever, right? In the end. But it's very good and very healthy and very important for understanding to take a mini situation and really understand the daylights out of it. I think you agree, right? So that's what I'm doing here, of course. And I think, by the way, my grandson would make the same argument as you. Come on, give me a break. I understand how to rotate this thing and reflect it. What else is there? Right? But I'm trying to say how you would systematically approach this problem. In particular, underline the role of group. We only need to understand the symmetries of the... Okay, so fixing 0. What are the objects of this geometry? Lines. 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 Right? And certainly, lines should be preserved in Euclidean geometry. A line should be mapped to a line. And so, as I learned very early in my life, you should ask the stupidest question you can think of: what is a line? And if you ask it long enough, you will say it is a one-dimensional sub-affine space of your two-dimensional affine space. Is it not? Is it not? What you've done is taken a sub-vector space of your... So remember, you had an affine space modulo... It's a question you were asking at dinner last night. You take... It's modeled on a vector space V. You take a smaller vector space in V, and you get a smaller affine space. Smaller group of translations and so on. So these things, lines, are the stabilizing lines means stabilizing, implies, not means, implies stabilizing the affine geometry. Doesn't it make sense? You're stabilizing all the one-dimensional possible sub-affine spaces. These are all copies of A1, and so on. The copies are here by these translations. It's a subgroup of translations in each case. Okay? And then you're led, yes?
So what would the definition of a one-dimensional affine subspace be? Is it the affine subspace model?
Right. So let's. She's asking, what is a one-dimensional affine subspace? It's a good question, right? So I think it's clear what the dimension is of an affine space, right? But it's modeled on a vector space, in this case over the real, so it's just a question of the dimension of the real vector space, right? So a one-dimensional subset, one-dimensional sub-affine space would be, in my mind, a subgroup of the additive group of the original vector space of dimension 1. So you have the...
But that's a subgroup about the affine space.
Well, every vector, okay, I'll even say it more precisely. An affine space is modeled on a vector space V. A sub-affine space, by definition, by my definition, I think yours too, is a subset which is contained in the obvious way by an orbit as an affine space model on a vector space W, which is a subvector space of V. Right? That's why I say you have all of these translations inside a two-dimensional translation group. You have all these one-dimensional translation things, right? It's somehow completely clear. I haven't written it down, but I think it's clear to everybody, right? It's a good question, Maria. So that's what a line is in affine geometry, right? And it's very interesting. It proves my point. We have a question, and this question, I don't know who asked this question, but I remember Kolmogorov talking about this in some things, and I think this question is serious. Characterize, it's a project. It's characterized with a Z, maybe, I hope. The transformations, so bijective maps. I can just write this in two-dimensional R2 with, let's say, call it transformations T of R2 with two properties, P of 0 equals 0, and T of any line, of a line, is a line for all lines through 0, containing 0. So, of course, a line is a one-dimensional subspace in linear algebra. By the way, linear algebra is an extremely new subject. The first linear algebra book was written in 1925, I think. And Euclid considered these problems in the year -400. So you see there's been a big development in mathematics since Euclid. And nevertheless, Euclid was able to understand quite a lot. So it's very amazing, actually. And before Euclid, there were great, I'm looking at you because I think you came from Egypt, actually.
Yeah.
You have to know these Greek guys, and he knows this since he's Egyptian by birth. Greek scholars of this period that I'm talking about, Euclid and before, Thales, for example, was even much before it, were quite often in Egypt. They were Greeks, but they were quite often in Egypt. So there's a heavy interaction between the Greek intellectuals, the Egyptian intellectuals. It's very, very interesting, right? Yeah. So this is a very interesting question, and I don't know the best answer to this question. I will say what the fundamental theorem of projective geometry is. If you have a mapping of a vector space, say Rn, which stabilizes 0, and you're asked the same question. It maps lines to lines. What is it? Right? Well, you need to impose a much stronger condition. If you have a line contained in a plane, then it should map the line to a line, and a plane to a plane, and that plane in the image should contain the line in the image. So to speak, respect the ordering of lines in planes and subspaces and so on. This is a huge condition, right? You're respecting the ordering of planes, lines, and so on. So it looks like a flag manifold a little bit, but, right? So you respect the ordering of lines contained in planes and so on. And the fundamental theorem of projective geometry says in dimension 2 or in dimension 3 and higher, I guess, such mappings are linear. And that is a deep theorem. And I don't know what the best theorem is in dimension 2. Yeah? And one of the reasons is, in dimension 2, if you take a circle and you say, what is a line? Well, it's 2 points across from each other in a circle, really. So this is coming very, very close to just some map of a circle. Yeah? And whereas in higher dimensions, you have these containment and so on. So it's a very interesting project, and so let me just write here, C, the fundamental theorem. Okay, so we are simple solution for this problem. Assume we have enough regularity when you see that word in mathematics, it means enough smoothness. You can imagine an arbitrary set is terrible, but a good, beautiful curve is you can handle. So you talk about smoothness and bad curves and bad sets and so on. We assume you have enough regularity to prove in our setting is what in our setting. Now, Maria, I mean by this in the setting of Euclidean geometry we're talking about. That T is linear. Okay? That's the reason we have the word linear mapping, because it takes lines to lines. So, you say we better have some notation. You say that GLV equal the set of T, which maps V to V, which is linear. T is linear. This is very bad. Set of linear mappings from T to T. Okay. Now, you're beginning, are you a physicist? You look like a physicist to me. Mathematician. Computer science. This guy, Mr. Weiss, was in computer science. But you see, Mr. Weiss had a nice idea to change that. Well, maybe you'll have to make the same good decision, just like this guy from Ho Chi Minh City. I used to call it Saigon, but that's only because I'm an old American. Where are you from?
Uzbekistan.
Uzbekistan?
Yeah.
Oh, that used to be in the Soviet Union,
Yeah.
but no longer.
No.
And you had at some time very much oil in Uzbekistan.
Yes, that's
I don't know still. Maybe not.
not much, yes.
Okay, what was I talking about? I don't even know. Okay. What was I talking about here? So, GLV is a set of linear maps. Okay. And that's the reason they're called linear. In Vietnamese or Uzbek. Uzbek is not, I mean, you grew up speaking Russian maybe, I don't know.
We're speaking Russian and Uzbek. Yeah.
Are these languages related?
No.
Yeah. Do Uzbeki people like Russians? I mean, or they hate each other?
No, not much, no.
There's
Yeah.
not too much hate. Depends who the Russian is. For example, Putin, for example. Okay, so, yeah, that's the reason it's called a linear map. Yeah. And the first thing you do as a stupid beginner in mathematics is you say, what kind of algebraic structure does this thing have? And you say to yourself, this guy who is a professor standing up here has told us some words, let's check them. Yeah? This thing is a group. Right? This is a group. And it acts on V. If you don't believe me, GLV acts on V. This is action mapping. Here's the action mapping. You take a transformation and you take a vector and you set it to the transformation on the vector. This is it. Good? And if you don't write that cleanly on your paper when you're working in mathematics, you screw yourself. You're in bad trouble because you'll make big mistakes. Yeah? It's not just being a pedantic person to write something cleanly. Right? It makes a big difference if you really see it cleanly what it is. Okay? It's a group and it acts on V. That's good. And it takes lines to lines. Right? So we have two groups which preserve the affine structure of A2. Well, A2 is modeled on R, so I don't write the R. The first group we're talking about is R2, the group of translations, plus. And the second group we talked about is GL2R. This is the group, well, GL, by the way, G stands for general, so there are no conditions on this at all, just invertible transformations, bijective transformations, invertible transformations. General linear group. When you see that, you say general linear group. R2 plus. That is the additive group of the vector space R2. This acts defining the affine structure on two-dimensional affine space. GL2R is the group of general linear transformations of R2. So I'll write here one more time, GL, this means GL of R2. That's a group and it acts on the vector space. Okay. So then you are led as a dream, you make a dream. So you must dream as a mathematician, and you shouldn't dream very big. I mean, they're very big dreams, and we were beginning in mathematics, so we were just hard to prob out. We were having some, in my office just now, some dreams, right? It's fun to have dreams. I hope you had fun in my office. We were dreaming a little bit. And we made little dreams that maybe we can prove. Right? So you should try to have little dreams that maybe you can prove. Right? So Prabhat and I had several little dreams. And I hope you can prove them. It'll be fun. Okay? But the dream is that the affine group of transformations, so affine group over R. So the group of affine transformations everything has been preserved. Affine transformations of A2 equals a product GL2R of two groups R2 plus. Oh my gosh, I'm scared. I'm scared. I wrote down something new. Okay? Now, let's start again. You had affine space. I was motivated to study it. I haven't answered Maria's question yet, what's the difference between affine space and Euclidean space? But I said, let's try to fix affine space first. Because the transformations are going to be bigger. They're going to be more. But somehow Euclidean space has to do with size and angles and so on. Affine space doesn't necessarily have to do that. So we looked at affine space. We had the translations. And we had if we take a translation, that's one. And we take a linear transformation having chosen crystal as a base point. Depends on which base point we choose, which linear transformations we get. And we hope that every element here is in the form, let's have some fun, TT. TT, just for fun, I write TT. So you should write things to make yourself laugh. Big T I just called was a linear transformation, and little t is a translation. So I'm saying somehow or another, every affine transformation, which preserves the affine structure of the affine space, should be a product of a translation and a linear map. That's all I'm saying. Yeah. And that's a very interesting statement. If you look at this, you should ask the big question. So I will write BQ here for the big question. Is such a thing a group? Yeah? You get the question, Marie?
Okay, so the elements in that, well, in the product.
Yeah, just product of two things, big T and
It
little
means
t.
that you first apply T and then you apply big T, right?
That's right.
But you can also do the other now.
That's right.
Okay, so it's going to be.
There are lots of things, well, we just saw more or less clearly that you apply translation and then you ask what you have left over as possible choice. And what you have left over is a big T. So we saw pretty clearly that the affine group is, the elements of the affine group are little t first and big T second. Yeah, that's what you agree with that. But as you say, you could translate, you could apply a linear thing first. If you have chosen Crystal or somebody as a base point, you have to do that first. And then apply the translation. Yeah? It may not be the same at all. Right? It may not be the same at all. Yeah? And that's related to the big question. Is the product of two such things, of two groups, a group? Yeah, and it has to do with exactly with Marie's question. Let's see if it's a group. Yeah, that means if it's really a group, then little t, big T should be around in big T, little t. Right? Right? Should be. So you see, by asking some sort of thing that looks like a pretty interesting big question, when is the product of two groups a group? It's a really interesting question, right? We'll talk about that. So preview. If you want to hack around and understand this on your own, and I'm going to talk about it soon, here we have, in the lingo of group theory, a semi-direct product. So you're learning words from me so you can talk to pros. Semi-direct product. GL2R. It's a product of sets, but it's also, in a good way, a semi-direct product of groups. So this funny symbol here means, what it means is that product is a group in this case. Okay? That's what it means, really. Okay? And you have to be lucky, and it's lucky in some sense, it's precisely Maria's point. She said, if we had here big T, little t, you also have something like a little t, big T. Right? And somehow, if you have little t, big T, you have to screw it around in another way and write it the other way. It's not so clear you can do it. And in this case, you can. Here we can do it because we have what is called a semi-direct product of groups. That is precisely the meaning of a semi-direct product. I'll talk about it in detail. Okay? Here it works. So, and I think the affine group, you will agree, I've written down all of the transformations you can find that preserve affine structure. So we have a little theorem, I'll write it down here in simple notation, F2, this is a group of affine transformations of the affine space over R. This is the group of affine transformations of A2 modeled on R of the vector space R2, this affine group is a beautiful product. Linear transformations, products of linear transformations. Having chosen Crystal as a good base point, or anybody, I don't care, Mr. Weiss, anybody else here, doesn't have to be in the front row, could be in the back row. Maria, we choose you as a base point, okay, with R2. Okay. So, i.e., every element is a form. Is of the form T, T. And you could have fun checking it. You could check it. She asked a question, you had to turn it around, and then you have to find a way to turn it back. You can't. Okay. Okay. The group of Euclidean transformations, E2, let's say R, the group of Euclidean symmetries of the plane of the set E2, which equals A2 as a set. Is smaller. Is smaller. I hope you see that. Because, for example, if you don't believe me, let's take a smaller than what? Than GL2R. I mean, if you're sitting at home at night and you've had cognac, half a bottle of cognac, and you're lying in bed like this, yeah, and you don't know what to do, and you ask this question, then you say, well, come on, the guy's not serious. If you take a transformation, a dilation, I talked about this last time, in GL2R, V that's mapped to lambda times V is not a symmetry of the symmetry. Okay? Right, of the Euclidean structure. Right, because I think even Maria, who's very critical of me here, would agree if we put 0 here and I double it. So I have to really map, I don't know how to double something, so map, well, maybe double or something, maybe double, I don't know, double, maybe. Right, here's a triangle in Euclidean geometry. Here's a triangle 1, and this is a triangle 2. And clearly triangle 2 is, I tried to make it 2 times triangle 1. And certainly in Euclidean geometry, these things are not congruent, we say. They're not. They're clearly not. So dilations are not in Euclidean geometry. Yeah.
Why is it not a symmetry of the Euclidean plane? I mean, it's certainly not a symmetry of the triangle, but of the plane itself.
No, it is a symmetry. It's an affine symmetry. I just wrote, it's a linear map.
Yeah.
Okay, so let's go through that. He said, why is it not a symmetry of the affine plane? It's a symmetry, I don't know, it's a symmetry of the affine plane.
Mm-hmm.
It is a map of the Euclidean plane,
Okay.
but it does not preserve the Euclidean structure.
Okay. Why is that?
It's a question of what's the Euclidean structure.
Yeah.
The Euclidean structure is such, for example, that size makes a difference, so that length is preserved. okay? And certainly length is not preserved by this mapping, right? Well, you pay your money and take your choice. What do you want to define as a structure of the Euclidean plane? I say it is Euclidean geometry. And I say that in Euclidean geometry, a big triangle and a small triangle are not congruent. Okay? So I don't allow that as congruent. So this is not a congruence, this is not a, okay?
Where does it follow from our definitions so far?
Nothing follows from our definition. We have not made a definition yet.
Okay, so we just defined that this is not now.
This is a statement of intuition.
Okay.
What everybody in this room believes is Euclidean geometry, that a huge triangle and a small triangle are not congruent. Right? That Jupiter and Mercury are not are of different size. Right? We're talking about size here, congruence in high school geometry. Okay. So we need a definition. This is what Mr. Weiss is talking about. Euclidean geometry. Or let's say Euclidean transformation. It's the same thing. So what is the definition of Euclidean transformation? If your mother asked you in Malaysia, I'm trying to remember you're from Malaysia. You talk to her on Skype at night, and yeah, she's not going to say that a huge triangle is the same as a small triangle. She's not stupid. Yeah, but if you put a triangle, and we're starting with if you put a triangle here, and you maybe I can make a funny thing like this in this triangle, right? That's an interesting construction, right? I claim those two triangles are congruent in Euclidean geometry. Your mother, I think, would understand how to do it. She would take the top triangle, rotate it around, and get the small triangle, right? That's what he was worried about before, about rotations and so on. Okay. Okay. So that's what we're dealing with. So we need what's the definition? And the definition is geometry preserving. And geometry I'm going to define here as length and angles preserving. I mean, wouldn't you say anywhere in the world, I mean, these guys back in Egypt in the old days, that they would say that. I mean, they knew how to measure length. That, you know, building the pyramids was an incredible thing, and they really needed some serious geometry to do this. And they certainly knew about length and angles, and knew that the good transformations preserve length and angle. Anybody here debate that? Are you, Nicholas? You're not debating that those are the good transformations.
Seems reasonable.
Hmm?
It definitely seems
Yeah.
reasonable.
Okay. We're going to take that because I said so. Okay. Okay? Okay. Here we go. How do you measure length? How do you measure angle? What are the transformations in GL2 of R which preserve length and angles? That's what we're talking about. We chose crystal. You're tired of me calling you a base point, but it's okay. I have to. So we chose crystal as a base point, because we know translations are okay with all of this, they preserve the geometry, so we're interested in the linear transformations which preserve the geometry. And so we've come to a question, which is a very simple question, which is the following. Question: what linear transformations in GL2R preserve length and angle? It's a reasonable question, right? What linear transformations preserve length and angle? Okay. Okay. So then another sub-question, sub-question 1. What is length? Sub-question 2. What is an angle? Yeah. Now I guarantee it, except for those who've thought seriously about this subject, that if you would come to me in an oral examination for this course, now, before thinking about it, because you're going to think very hard for this whole period, but before thinking about it, and I ask you, you come in and you say, Euclidean transformations preserve length and angles. And then I say to you, what is length? I think a majority of you might have a good guess at what is length in Euclidean geometry. Right, you guess. But I think a big majority of you would have great difficulties with the notion of an angle. Okay? Let me claim again. What's an angle? Huh? I don't know. What's an angle for you? Yeah, okay. She just went like that and so on. Yeah. It's a non-trivial thing. It took a very long time in mathematics to understand what is length and what is angle. It took a huge time in mathematics to do this carefully in a nonlinear setting. This is a linear setting. In a nonlinear setting, this is a fundamental understanding of a man named Riemann in the 19th century. What is length and what is angle for Riemann is the so-called Riemannian metric. Gauss himself understood basically intuitively what this is, but did not formulate this as well as he could have. This is a non-trivial thing. Riemann was non-trivial. His teacher Gauss was highly non-trivial also. Right? Don't think that these questions are trivial. Yeah? Because you cannot, I guarantee you, without having a teacher telling you the answer, you could a priori would not be able to answer these questions. Okay. Here, we had, and it was interesting that Apik last night was saying, we were chatting, while you have the standard inner product, and you learn all this in school, and it's true. I do not know the history of this inner product, but it's probably rather modern. Here, we have a certain standard inner product, which is a mapping on R2 to the real numbers. R2 cross R2 to the real numbers. I only have to talk about R2 because I'm only having to talk about these things, R2 and R2 to the real numbers. And you look at this thing, and everybody says, oh, I understood that at school, man, that's trivial, come on, give me a break. Oh, and the notes I write, this is V. V1, V and W, right here, two vectors. I understood that at school, there's nothing to it. All right, that's the standard inner product, right? Right? Okay. And once you have the standard inner product, you say, well, okay, let's see, the length of a vector, and I always tell everybody it's much better to talk about the length squared of something. And the reason is, if you introduce a square root, you're introducing a function that is really singular. You understand square root has a bad singularity as 0. And so you should always, if possible, talk about the square of something. Everybody knows this is v1 squared plus v2 squared. And so you know this is vd. Right? Isn't that right? Yes, this is the length squared of something. Okay? And what's an angle? So this is somehow, this is the length of v. And now what's an angle in terms of measurement? This is the length of it. And she was going blah blah. She's a physicist. So she should know better than blah blah. Right? Because physicists, by the way, you mathematicians, have to know physicists compute beautifully. They compute all the time. But the danger is the brilliant physicists are so brilliant, they know what they're computing. But the physicists who are not so brilliant just compute and don't know what they're computing. So you have to ask them what the devil is. It's, what are you computing? She's brilliant, I'm sure. Okay. What's an angle? You know what an angle is. Cosine theta. Well, she went blah blah. Here's v and here's w. And here's theta. And cosine theta is equal to inner product VW. It's I'm trying to push for automobiles sold in Germany. Inner product VW. Scaled. So the norm is 1. Right? And of course, you know what you always like to do. You say, well, what I like to do, you learn this in high school or engineering courses. I like to scale these back to unit vectors. So here's a unit vector here of v divided by norm v. And here's a unit vector here, w divided by norm w. Right? And what this really means is I scale back to unit vectors. And that's the same as the angle by the unit vectors. That's a little bit what you were doing here. You had 2 unit vectors, and of course you're coming close maybe to the circle, and maybe you're coming close to saying an angle is a point on the circle. Maybe. And so you somehow want to know how to parameterize what is an angle and so on. And now you say, okay, she was trying to make this a unit vectors here and everything's cool. So what did she do here? Let's suppose this was Crystal. Crystal, what did Crystal do? Crystal do here. You see, you don't ask those questions and I know it. What Crystal did is said, well, I have to take the norm inside the square root. Inside the scalar product, right? What did Crystal use there? That you can take the number inside the scalar product, right? Yes. Nobody here would ask this question besides me. Well, a few other people maybe. Okay? What Crystal used is the first step here, the key first step in a scalar product is bilinearity. Of the scalar product. Okay? That's what she used, actually. What does it mean by linearity? It means A V1 plus B V2 W equals A V1W plus B V2W right? This is linearity in the first argument. Bilinearity means in both arguments. Both arguments. She used that, basically. You can go in and out of the inner product. You use that. Okay? Now I'm going to give you another bilinear form. I'm going to give you another one. She's tired of this class. So I'm going to give you another one. Let's have some fun. Here's another one, just for fun. Let's say B is equal to x1, x2, and W is equal to, in numbers, y1, y2, right? And so let's say the bilinear form B of BW, this is called a bilinear form because it's bilinear, is equal to x1, y1 minus x2, y2. You see? First of all, if you're Crystal and you said, what I use is bilinearity, then you should write down what bilinearity means. It means linear in both arguments. Bi means both. Linear in both. Good, she used that. She's a physicist. Yeah. And so here's another one. Well, wait a minute. Let's see what the norm is. Let's see what the B norm is of V. The B norm squared, because I can't do anything else, but I don't want to take a square root. What is it of V? It's x1 squared minus x2 squared. Is it not? I let V be W and then also here, I get that. And what's wrong with a norm like that? What's wrong with length like that? It could be negative. And then people, it's good, Mr. Pham, good answer. Yeah, he's really worried about it when he sees a norm should not be negative, right? And then Crystal says, actually Deepak says, well, my friend, I'll give you his initials, and not only his initials, but this guy's initials and many other people's initials, says, well, here, let's make it in dimension 4. Yeah? Let's say x is equal to x1, x2, x3, x4. Oh, why not? Let's call this t. T. Yes? T. And then let's say y is equal to y1, y2, y3, in 4 dimensions, I don't care, any dimension is good, f. And now let's say x, y, oh, let's write b to be careful because it's not the standard thing. X, y is equal to x1, y1, that's great. x2, y2, that's great. x3, y3, that's great. Minus t times x. That's the simplest thing in the world to go from my example to that example. You agree? Oh, let's make it even be a little bit more fun. Let's put a number here, which can be some number. T times x. Some number. No, it's a number, it doesn't matter. It could be 1, but we call it c. And now let's see, the norm of x squared with respect to this bilinear form is x1 squared, great, x2 squared, great, x3 squared, great, minus c times squared. And Mr. Pham was worried about that because it could be negative, right? Do I have the signs right? I hope the space variables.
Well, I would write c squared.
Huh?
I would write c squared.
Oh, you need, okay, so to emphasize that c is positive, I'll put c squared. Oh, let's see here. No, c squared, yeah. Mr. Pham is starting out in mathematics, and he likes mathematics. He doesn't know anything about physics yet, but he'd like to know what these initials stand for. One, E stands for Albert Einstein, L stands for Lorentz, and there are other numbers. This is the Lorentzian geometry that you need to understand, Minkowski geometry. So Minkowski is a great name. He gave lectures in Zurich. Zurich is a place in Switzerland, and he gave lectures in Zurich. And Einstein was a student of in his lectures. You know that. Einstein was a student of Minkowski's lectures in Zurich. And of course, Minkowski understood this thing very well. And somebody asked Minkowski, was he a good student? Or how was he? And Minkowski said, fortunately, he never came to my class. So it's a statement about a genius. You don't want him to be influenced by your lectures on something, right? You want him to be creative and so on. So these are great giants of the past, these physicists and this great mathematician Minkowski. And you see, this is the appropriate bilinear form for relativity theory. It's some word in physics that she knows. Yeah, right? You know that word. So it's not so clear what is the right geometry. The geometry is given to you by the bilinear form. It's your angles and length. It could be the length is negative. That's the frightening thing. I don't know what that means. Yeah? Okay. So, geometry is given to you by a bilinear form, and Euclidean geometry is given to you by a bilinear form which is positive definite, and there is effectively only one such on the plane. So, let me state that. So, a bilinear form B from on a vector space, a real vector space, so let's just make it abstract, say a real valued bilinear form on a vector space, B is said, finite dimensional, if you like, just R2, is said to be positive definite. So let's discuss only symmetric bilinear forms. So symmetric, we really need this condition very badly. Symmetric means it doesn't matter which way you do it. It's said to be positive definite. Some people just say positive. Exactly when Mr. Pham's not worried. If and only if V of VV is positive, except for V equals 0. I mean, it's okay, length. So that means that length squared with respect to V is always positive if V is not 0. So it's good that Maria just left, because now I have freedom to say what I want to say. Yeah? The geometry of the Euclidean plane is determined by a symmetric positive definite bilinear form, which in fact can be taken in normal form to be the classical inner product. Let me write that sentence on the board. The Euclidean geometry on of E2 is given by a symmetric positive definite. Mr. Pham is happy. Bilinear form. We write it like that. Okay. Maybe I'll write it B. I'll write it B. Write it B, and let's emphasize on the Euclidean plane, any vector space. So where this is a vector space of R2, so this is equal to R2 is a vector space after translation as R2 cross R2. You're tired and late afternoon, but what's the next question? The question is, so, no, what does it mean then? So the length of something, of a vector b squared, is just BVB. And cosine of an angle is equal to BV, and theta is the angle between two things, V and W. And it's oriented. So you get a side difference, so I'm talking about the angle from V. This is an oriented angle. So theta is an oriented angle. So we know what the cosine of an oriented angle should be. It should be B of VW divided by norm of V length of V length of W, or by the unit vectors. Isn't that a good idea? I've now told you what is, it's too bad Maria left, because I've now said what is a Euclidean geometry on R2. Here it is. It is set. E2 are identified by R2 when we use crystals of A point, equipped with a structure which is this bilinear form, and it gives you length and angles. Now I challenge you to write a very easy fact that you can prove. I think the following fact is provable. So check it. Check it. Up to isomorphism, there is only one such form. Yeah? And in its normal form, we put it in its normal form in this form. It is exactly the classical standard Euclidean structure. I think that's true. Up to some sort of. Now, you know the people, is anybody here from Africa? I don't see anybody from, oh yeah, you were from Kenya, yeah. So the people, it's the people in Africa, I don't know, is it really true? So people here in northern Germany, oh, well, we can do that as an example. I don't know, do you think it's true that people in Kenya, for example, tend to be taller than the people here? I mean, you're a lot taller than I am, so do you think it's true? Oh, I wanted an example. Is it? I think, okay, here we go. I could make some terrible examples about fat people in the United States. But, yes. Oh, here are these Vietnamese guys. I think people in Vietnam, the usual people in Vietnam are shorter than people in northern Germany, right? You're an example, Mr. Weiss is an example. Yeah, well, maybe you're a bad example. Hmm?
I'm not from Northern Germany.
Ah, okay. So it's even worse if you find somebody from the north. Right. So it's a question. It's a question that people. We say to him, well, he's standard, so he's length 1 in Vietnam, and he's standard, so he's length 1 in Germany. We make the standard length equal to 1. In Kenya, I don't know whether you're big or small in Kenya. Right? About standard, probably. Yeah. Okay. So you're in the Kenya form. You're length 1. In the Vietnam, like the Egyptian form, they're all about standard. Would you say? I think also. Well, they're tall Indian people, though. It's funny. Maybe you're standard. I don't know. You standard? Okay. I'm trying to say that different places use different definitions of length, right? And of course, you can scale this. You can multiply this notion by length by 17. And this guy, no, we take this guy from Vietnam, and he's length 1 in Vietnam, and we multiply his length by 17, and he's equal to Weiss's length. Right? So it doesn't, right? This is okay. Same thing with this Egyptian guy. I don't know about the people in Egypt. Are they big or small? Oh, the ancient Egyptians. It's interesting to know that were they bigger. You looked into these sarcophagi.
Yeah, they draw themselves as two, but we don't know if they are.
You think is that right?
Yeah.
Oh, that's interesting. So anyway, up to isomorphism. So you see, there's an isomorphism from northern Germany or Frankfurt, Germany to Vietnam. The isomorphism contracts the notion of length, right? But up to that kind of isomorphism, yes. There's only one. So we only use this one thing. So we use this thing as the normal form. This vector A, vector B is A1, B1 plus A2, B2. This is going to be our standard structure. Okay? We're going to say we're here in northern Germany, and that's going to be our standard structure. That's it. Okay? On R2. Okay. And if a transformation in GL2R stabilizes this structure, or let's say fixes this structure, this inner product, then we say T is an isometry. Of the Euclidean plane. I claim that the correct group of linear transformations for linear geometry, in the sense of Euclid, is the isometries, those which preserve length, angles, and so on. What does it mean, isometry? Let's write it down. Isometry means, this notion means, T of VW equals VW for all V and W. It doesn't change the notion of length, and it doesn't change the notion of angle. And it's linear, right? Because we are only considering the stuff that comes from Gross base point. Otherwise, we have a translation, right? So we're considering the linear isometries. So let me even emphasize here, we're talking about it all the time. Let me write here, linear isometry. Just so we're talking about the. So, because starting with a square, you come to a question. Describe, or a project. Better word is a project. Small project. Describe the isometries of the Euclidean plane, so linear isometries of the Euclidean plane, It's a reasonable thing, right? I mean, what are those transformations which preserve length and angles? Isn't this, I mean, I think it's the fundamental question that we have come up with now. I'll lecture a little bit more, and then you're getting tired. Then we go to lunch and talk a little bit more. Okay. Let's take the standard basis of R2. Let's call it E1 and E2. These are the standard basis of R2, the x-axis and y-axis. Here is the point E1, which is the point 1, 0, and here's the point E2, which is the point 0, 1. Okay. Let's let T be an isometry. Okay. T of E1 is equal. Let's make these things column vectors. So it's the usual thing to use column vectors from school, right? Let's use column vectors. You don't care. They existed in Vietnam, I hope. Column vectors. Okay. T of E1. Let's say it's AB. Yeah? Let's say T of E1 is AB. How long is AB? How long is E1, by the way? 1 inch or something, 1. Therefore, the length of AB is 1, because it's an isometry. Oh ho, oh ho, oh ho, oh ho. The length of this thing, E1 squared, is A squared plus B squared is 1. Are you happy? That's interesting. Okay, we draw a picture. Here's E1, and I'm going to make a circle. If I'm lucky, I'll get a good one. And here is the point E1 is equal to 1, 0. And here's the point AB on the circle. Immediately draw the geometric picture of what you have at hand. What about T of, let's say T of E2 is equal to CD. How long is E2? 1. How long is CD? 1. It's an isometry. You see the word measure in metry. that means it should measure the same. Isometry. It's an isometry, but so T of E2 is equal to CD, and this should be also 1. Okay? So let me see here. I'm going to draw a nice picture. Let's see what happens. It should be, should it not? This is CD here, and this is T of E1 here, and this is T of E2. Yeah? Yeah? CD. What is the angle between E1 and E2? If you've done any geometry in your life, you know the first thing you understand is right angles. Isn't that true? This angle even has a special notation. Right angle. The angle is a right angle. What does it mean that a vector V is perpendicular to a vector W? That's what there could be some other vectors. What does it mean in terms of the measuring stick VW? You've done this calculation, I hope, many times. Right? The two vectors are they're perpendicular if and only if. Scalar product. So this is built into the scalar product. Right angle geometry, right? That's the reason I carefully tried to draw a right angle there. Okay? Equals W. Well, let's see. Then we learn from school and learn from a little bit of mathematics at Jakobs University that the best thing to do is to summarize this data in what is called as a matrix. Right? Summarize this data in what is called a matrix. It's a magnificent thing, a matrix. The matrix of this, and be careful, the matrix, it's not the transformation itself, the matrix of this thing, T, in the standard basis, with respect, so this is respect to the standard basis. Well, you do it like this, at least when you're a beginner. You say, where did E1 go? Where did E1 go? That's a song, right? You would never know. I'm the worst singer in the world. Where did all the people go? It's a song from the hippie movement, which I grew up in. You don't even know what it is.
I know that song.
Yeah, you know. But I was in San Francisco at the time, and you were not born. So I had a big advantage. So, okay. E1 goes to AB, right? Right? And this thing goes to CD, and E2 goes to CD. Right? Isn't that what happens with a matrix? Make sure you know that. That's what happens with a matrix. And now you use the property that AB is perpendicular to CD, and the length of CD is 1. And you check that this is either AB, that can be anything, minus BA, you can check it if you don't believe me, or AB, let's see, minus AB, did I get this right? Yeah. Minus this thing, B minus A. If you don't believe it, at least look here. The scalar product of these two is A minus B, BA. Right? So that's 0. It has to be because they're perpendicular. And here it is again, I say that minus. You have no choice. You have a little choice. You have a little choice. You could go AB here, and then CD could be down here. Don't you agree? It could be down here. It could be a rotation which is oriented in the other way than the original orientation. So there are two possibilities for these things. They're called AB. This is a positive orientation on the usual the usual rotation. And this is the negative orientation. And that's it. That's all the possibilities. And now, coming to the end of this lecture, I see you looking, I was going to quote you. You're disturbed? Well, you may be disturbed in the other sense of the word, but I don't think so either. Okay? Where are all the reflections here? Where do they all go? Right? There should be here, because reflections should preserve length. Right? And now let's see, what is a reflection? Let me think, what is a reflection? This is a joke. I'm reflecting on the notion of reflection. So, well, all right. So what is a reflection? Here's E1, and here's E2, and E1 goes up to E2, and E2 goes down to E1. Right? Now let's look at this thing here. That means that E1 goes to E2, so that's the matrix. This thing is called R for reflection. So the matrix of R is 0, 1, because E goes to E2 and 0, 1 is E2, so that's E2, and now I have to put it here, and that's 1 here. All right. Now, every physicist in this audience will immediately compute. Yeah. And it's a good idea to compute and see what happens. Just see what the devil happens. I mean, compute. Well, okay. Let us compute. Let us compute here. A squared plus B squared. I told you that had to be 1 because it had to be in length 1. Every physicist will say, well, I'm looking at this matrix. How do I see A squared plus B squared in this matrix? The determinant. The determinant, right? The determinant is 1. The determinant is 1. Uh-oh! What's the determinant here? Minus 1. Yeah? What does determinant measure in geometry? What does determinant measure in geometry? What does determinant measure in geometry? You have a vector V, which is V1, V2, and you have a vector W, which is W1, W2. And you say, well, I'm going to put this thing in a matrix, and I get a determinant. I have V1, V2, W1, W2. You should ask yourself, you've seen these Mickey Mouse things in high school, you just do some stupid calculation with a determinant. You should ask yourself, what in the devil is the determinant? Right? Do you know what a determinant is? Do you know what the determinant is? Do you know what it is? It's the area between those two vectors. You know that. The determinant measures precisely the area between these two vectors. Right? And it's completely clear that the area between E1 and E2 is 1. So the determinant is here 1. Uh-oh! The determinant here is minus 1. Okay? That just told you that area is a thing that must be oriented. Right? There's such a thing as orientation. The area between I can't do it with my finger. The area between E1, there it goes. Between E1 and E2, if this is E1, yeah, is 1. But if you count E2 as being first, and then E1, the area is minus 1. And I'll tell you why that is. It's that because when you were in school, you took a Möbius thing, right? And you start out with a little frame on the Möbius thing, and you take it around, you move it around, and you come out backwards. Yeah? this going around the square, the Möbius thing, does not preserve area in any sense of the word, and the reason is the Möbius thing is not orientable. You cannot define area on the Möbius thing. It's interesting, right? So already we see here that if we have R is a reflection, and we have all of these rotations, then we see here what is the answer to our problem. What is the linear isometry group of the plane? And I will stop at the perfect timing in some sense. Let me stop now. So you will check easily. And so here we go. So the notation O, 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 O to R. This is the set of T in GL to R that we are interested in, such that T preserves the inner product, namely geometry. The reason you call it O is because, well, for one thing, this is called the orthogonal group. And one reason that it's called the orthogonal group, you see it right here. The column vectors in this matrix are orthogonals. Okay? So it's the orthogonal group. This group contains something I'll call O2R plus. These are the isometries of the plane. This is the elements of this, of the isometry group, which preserve orientation. Orientation, and you know I just told you what that is. That means the determinant. Right? And if you like, the full orthogonal group, this is what we're interested in, which is the group of linear isometries of the plane, is equal to this group of rotations. This is a funny symbol. The group generated by reflection. This is a group of order 2 generated by reflections. Generated by R. Reflection. I just proved it here. And now the final statement is the group, the isometry group of the Euclidean plane, E2R, is just as before. It's the orthogonal group of the linear transformations, which we can consider, because we took crystal as a base point, which is semi-direct product with R 2, I will tell you, it's a product of two groups, we will talk about what that means later. But, oh, I hope I did this, yeah, it's correct. Okay? And now, I've given 2 long lectures and you're dead tired, I'm sorry. We go eat, drink a bottle of cognac, smoke a cigar. Yeah. But we started with the question, what are the symmetries of the square? And we came to the question of what are the symmetries of the Euclidean plane? And I worked very hard to define the notion of symmetry as the action of a certain group. The groups are translations and linear groups. A linear group of symmetries is a so-called orthogonal group. Right? This is now the question, and it comes back to Mr. Weiss's remark about rotations and reflections. And now the exercise, which you can easily see in the notes, and it's a fun exercise, is the question is now, because we took Crystal's base point, I have to decide, if this is 0, what are the transformations in the orthogonal group? So the matrices are of the form, we know what they are. So of the orthogonal group, either rotations or reflections, what are those operators which stabilize this? And so the group of symmetries, so the group, say let's just write it, the group of symmetries here, let's write it, of symmetries is rotations in the group of order 4 times a reflection group, and this is a group of order 2. Right? Reflect, and again reflect the same. Rotate 4 times, and you're back. And now I ask you, is this really, it's too bad Maria's not here, we're complaining about, is this really a group? Yeah, check it. So everything can be uniquely expressed as a rotation times a reflection. It's a group of order 8, obviously. Group of order 8, with the 2 reflections and 4 rotations, group of order 8. Check it, that it is not commutative. I hope you understand that if you have first a rotation and then a reflection, it's not the same as first a reflection and then a rotation. I think you can see that, right? So it's not commutative, but it is a product of 2 groups, and one of them is much better than the other one. I think in some sense the reflection is better. And we finished in 2 lectures the project of the symmetries of the square. So let's have dinner.